It's a great day for Gauss-Bonnet. In this video, we're going to talk about surfaces, specifically the plane and the sphere, and how they're different because the sphere is curved and the plane is flat. We're then going to derive a formula for the area of a polygon on the sphere in terms of its interior angles. This formula will be very useful to us later. Let's dig in. Okay, it's a great day for Gauss-Bonnet Video 2. We're once again in Bozeman, Montana. It's a rainy great day for the Gauss-Bonnet theorem here. Okay, so last time, what did we do? We talked about polygons in the plane, and we came up for formulas for the sum of the exterior angles, which always equals 2 pi, because we make one complete revolution. And the interior angles is pi times quantity n minus 2. And then we use this to prove Pick's theorem, which gives us a clever way to compute the area of a polygon on the Z2 lattice, where we count the number of interior vertices and the number of boundary vertices, divide by 2 and subtract 1, and that tells us the area. Did we get any notes from last time? We did. So I showed this video to some friends, and what did they say? Well, we got Bonnet Macaw was a big hit. So he's back again, and the other feedback was we need to write a little neater, so noted. So as always, we appreciate the notes. Okay, so this time, I know at the end of the last video I said I was going to talk about the curvature and the Euler characteristic, but we're going to slow down a little bit and just talk about surfaces. Two surfaces that'll be important to us is the plane, R2, that most of us have spent a lot of time working on with the plane, and then the sphere, we'll denote this S2. And ultimately what we want is a formula for the area of a polygon on the sphere in terms of the interior vertices. Oops, that was my highlighter. And so this video will culminate in a formula for that. So that's our goal. So here's the statement of the Gauss-Bonnet theorem, and today we're focusing on the symbol M. It's going to be a surface for us, but it can be a manifold or a higher dimensional object or a lower dimensional object as well, but most of the time it's going to be a surface. And so that's the first symbol we want to sort of consider today. And then next time we'll talk about this K, which is curvature, maybe geodesic curvature, and then we'll talk about the Euler characteristic a little bit. So for most of our applications, we're going to consider our surface to be a disk, so just something like this, or the sphere, so a hollowed out ball. And so our disk is a subset of R2, and the sphere is a subset of R3. And one first thing to notice is the disk has a boundary. And if it's the unit disk, this will just be the circle with no interior, and the sphere, no boundary here. So when we consider the Gauss-Bonnet theorem, we're considering these two terms here. One is the boundary of our surface, and one is the interior of the surface. So when we consider the Gauss-Bonnet theorem applied to the sphere, we won't have this term because we have no boundary. So when we want to work with these surfaces, often we want local coordinates. So for the disk, this is a two-dimensional object, and we can think of this is the set x, y, such that x squared plus y squared is less than or equal to 1. And if we want to move around in our disk, usually just the coordinates x and y are going to be sufficient to tell us, any point on here. We can say, well, it's a subset of R2. So we can say, well, where are we in R2 and where are we on our disk? Maybe some stretching or bending, but that can be accounted for. The sphere is a little bit more interesting. So this is a subset of R3. So we can think of this as an x and a y and something like a square root of 1 minus x squared minus y squared. And this will give us sort of our northern hemisphere, so we can imagine that sitting above our sphere. And if some action is happening in the northern hemisphere, we can use this map or these coordinates to describe what's happening in a nice way. So moving around in the northern hemisphere, we have nice formulas for where we are. But sometimes we'll move, between a northern and southern hemisphere, and we can also get, coordinates for the southern hemisphere. So we could have something like this, and this would be x, y, the negative 1, oh, what are we, yeah, oh no, that's okay, 1 minus x squared minus y squared. So this would be our southern hemisphere. And you say, okay, that's pretty good, but maybe, something happens where we're moving across the hemisphere. How are we going to jump back and forth? Well, we can keep going, and we'll get left and right, and we'll call these things charts. Sometimes these are called charts. And if we transition from one chart to the other, there's a way to account for that. I won't get into the details, but often we have formulas like are drawn here. And if we want to compute something in the future, we'll want to compute curvature, we can use these formulas to compute curvature. Okay, so we can cook up local coordinates for the disk and the sphere in sort of a natural way. So other surfaces, that we won't use that much, but maybe you've seen, we could have the torus. If you know an application of the Gauss-Bonnet theorem applied to the torus, I'd be very interested in seeing that. You could have a many-hole torus, something like that. We could have a non-orientable surface, so something like the Klein bottle. Is also a surface that we might want to work with. We could have a manifold with a boundary, so some sort of torus with a boundary. So these are all surfaces that one might consider. I am aware of an application of the Gauss-Bonnet theorem to the surface with constant negative curvature. So maybe we'll talk about that if time permits. Okay, but our primary surfaces that we'll see in most of our application are the disk and the sphere. And even our first application of this turning tangent theorem, we can consider that as being a case of the Gauss-Bonnet theorem applied to the disk. So maybe we'll talk about that at some point. Okay, and then we have potentially other surfaces. Okay, so let's compare the plane and the sphere a little bit here. So the first thing to consider is triangles. So in the plane, if we have a triangle with interior angles here, one thing to notice is if we scale the triangle, the angles don't change. So I could have a small triangle with the same angles or a large triangle with the same angles. And of course we know that in the plane, the sum of the interior angles is going to be pi. And we can see this by drawing a parallel line through the opposite vertex and using alternate interior angles here. But this is not necessarily the case, or it's not the case on the sphere. So if we consider a triangle here, we could have a triangle with all right angles. And of course, right angle is pi over 2, so this would be 3 pi over 2. Is the sum of our interior angles here, so not the same. Another difference is that if we look at two non-parallel lines in the plane, they intersect one time, but on the sphere, they intersect twice. So once out front and once at the antipodal point there. So triangles behave differently, and two non-parallel lines also behave differently. And this is somehow because the plane is flat and the sphere curves around. It has curvature. Okay, so when we draw two non-parallel lines on the sphere, we get this nice shape that kind of looks like a moon. So we call it a loon. And we'll just use the fact that the area of a sphere of radius r is 4 pi r squared. So for us, we're dealing with the unit sphere here, so just 4 pi. And we'd like to calculate the area of this loon in terms of our interior angle alpha. So if our alpha is 0, well, we get no area in there. And what's another thing we can observe? If alpha is pi, the area is going to be 2 pi in one of these things. That'll be half the sphere. Or if you consider since we have 2 copies of the loon, the total area would be 4 pi there if you're counting both of those. Okay, and another thing to observe is that this is linear. If we split our angle into 2 alpha 1 plus alpha 2 equals alpha, the area of the loon formed by alpha 1 plus alpha 2 is equal to the area of the loon formed by alpha. So this thing is linear. So we'll say, actually I'm going to say not 2 pi, let's say 4 pi. That's count both copies of this thing. And so we'll say our area of our loon with angle alpha is going to be 4 pi. Okay, so now we can use this to calculate a formula for the area of a triangle on the sphere in terms of these interior angles, alpha 1, alpha 2, alpha 3. And what do we notice here? Well, we're going to get 3 loons, and we cover the sphere entirely, but we cover it a bit too much. So we're going to cover each one of this triangle 3 times, and we're going to cover the antipodal triangle also 3 times. So the area of our triangle relates to these interior angles. So we know the total area of our sphere is 4 pi, and that's equal to our 3 loons, so 4 alpha 1 plus 4 alpha 2 plus 4 alpha 3. But we're counting a bit too much because we're covering our triangle 3 times on the front and 3 times on the back, but we only want to cover it once, so we'll get minus 4 times the area of our triangle here. So really there's 6 coverage, but we want 2 of them to account for the surface area of our sphere. So if we solve this for the area of our triangle, everything has a factor of 4, so the area of our triangle is equal to alpha 1 plus alpha 2 plus alpha 3 minus pi. And you can check with that example we did up here that this is what we want, because that would be what, 1/8 of the sphere there. So we get pi over 2, and everything checks out. Okay, so in the future, we're going to want to consider polygons that are not triangles. So we're going to need a fact here that every polygon with n vertices can be triangulated with n minus 2 triangles and no additional vertices. And this is true on the plane and on the sphere. In the plane and on sphere. The proof is maybe easier to see on the plane, so we consider, I'll sketch it here, consider the convex hull of our polygon, and then we take the point that's furthest to the right, and this edge from that point to the point on our convex hull must be contained in our polygon, and then we can use an inductive argument to show that this thing contains n minus 2 triangles. So here I have, 4 vertices, and the number of triangles here is going to be 2, which is n minus 2. Okay, so maybe you've seen that before. But this also works on the sphere. And so to get our formula for the area of a polygon on the sphere in terms of these interior angles, we can just decompose our polygon into triangles and sum up the area of our triangles. Yes, some of our angles will be split, but the total sum of the angle will appear in some triangle, and that's okay. Okay, so our area of our polygon is going to be the sum of our area of our triangles. And we know we have n minus 2 triangles. So if we just sum up our alpha i's, I equals 1 to n, and then we're going to get what, minus n minus 2 copies of pi here. If that's too many minus signs, we'll get what? Sum I equals 1 to n alpha I plus 2 minus n pi if you prefer. And this is the area of a polygon on the sphere. So this will be useful to us later. So this is kind of like our highlight. Oh, we haven't been putting in our macaw. Well, let's call this a proof and say, just so he makes an appearance at least once in this video. Or I guess this is his second appearance, so we'll say that's a proof. So we get this nice formula for the area of a polygon on the sphere in terms of the interior angles, and we'll use this to compute curvature later on. Okay, so we talked about what did we do in this video. We mentioned the Gauss-Bonnet theorem briefly. Mainly we're talking about the surface that appears 3 times in this formulation, and we use m. M stands for manifold here, but you can think of it as the surface. In most of our applications, we're going to consider the sphere or the plane, and we looked at triangles behave a little bit differently, and 2 non-parallel lines also behave a little bit differently. And we came up with this nice formula for the area of a polygon on the sphere in terms of the interior angles. Okay, next time we'll talk about curvature. So thanks for tuning in. It's a great day for the